Hello again. Today we're going to go ahead and start looking at some more things with quadratics. Specifically, we're going to be looking at graphing quadratic equations. So when we're talking about graphing quadratics, we're talking about our functions that we saw before, x squared plus bx plus c, and now we're going to be graphing these. And the general shape of this is something called a parabola, and we'll talk about that more a little bit here. Okay. So quadratics, we say they're nonlinear because they're not in a straight line. There is a curve, and again, this curve was called a parabola. All right, is what we mentioned earlier. Okay, a graph is called a parabola, and we know this right here is what we call our standard form of a quadratic equation: ax squared plus bx plus c. That should be reviewed. Okay, so our shape is a parabola. We know that they're going to be symmetrical about a line called the axis of symmetry. So if I draw a rough graph of a parabola, okay, it's kind of this U-shaped graph, but if I were to draw a vertical line straight up and down the middle, if you notice the left half is exactly the same as the right half, and that's what we refer to as the axis of symmetry, meaning if we were to fold our graph along that line, both sides would look exactly the same. Okay, so where our axis of symmetry crosses our graph is at a point called the vertex. So in this case, our vertex is the very bottom of our graph. And this is going to be an important part that we'll talk a lot about with our functions. All right, so how do we go ahead and graph these? Well, we can always do an XY chart. Okay, so we can plug in values for X, okay, and then get out values for y. That's always going to work. That works for every graph, every equation you could ever come up with. However, there is going to be some other useful information that we're going to talk about. Our axis of symmetry. Okay, how can we find the line that we just talked about? Also, using that to find our vertex. Okay, intercepts. All right, are also easy things to help us graph. So these are things we're going to talk about this chapter as we go along. All right, so let's start with our very first basic equation, y equals x squared, or kind of what we can call our parent function. And we've used this terminology with a lot of our other graphs before. We call it the parent function because this is the most basic, simple, plain graph of just x squared. So if I were to do an xy chart, all right, if I plug in -2, this would be -2 squared. -2 times -2 is +4. Okay. -1 squared would be 1. 0 squared is 0. 1 squared is 1. 2 squared would be 2. Excuse me, 2 squared is 4. All right, so if I graph these now, -2, 4, -1, 1, 0, 0, 1, 1, 2, 4, you can see what our curve's going to look like. And our curve's going to look roughly something like this. Okay. So now if I were to ask you, where is our vertex? Our vertex is the bottom point here. This would be at the point 0, 0. Okay? And then our axis of symmetry would go through our vertex here. This would be the vertical line, so it's x equals 0. Okay? So now here's where we're going to talk a little bit more about some of that other information that I mentioned. So first of all, our axis of symmetry. The equation to find this is -b over 2a. Okay, and again, you're just grabbing these from your standard form of your equation. Okay, so whatever your a is and your b is, those are the values you plug into this equation. Okay, then to find your vertex, well, hey, we know that the x-coordinate of your vertex is the x-coordinate, or is the equation of your axis of symmetry. So to get the vertex, you just take that number and then plug it into your function. That's what it's saying here. So it's like, all right, I'm going to find what that point is, plug it in, and whatever I get out, okay, it gives me the y value of my vertex. Okay, and then also your y-intercept, okay, is always going to be whatever your c value is. So whatever number you are adding or subtracting to the end of your function, okay, when you're in standard form, is going to be your y-intercept. Okay, so let's look at a graph here, an example. So I have y equals -2x squared. Again, I could do my xy chart, but I'm going to go ahead and use some of those other things that we talked about. So first of all, I'm going to find my axis of symmetry. And again, our equation for this was -b over 2a. All right, well, our standard form, once again, ax squared plus bx plus c. All right. So my b value, do I have any regular x's? I don't. So my axis of symmetry would be negative 0 over 2 times 1, which would be, well, 0. Okay? All right? So my axis of symmetry is going to be at x equals 0. Now, how does this help me? And the reason I graph this is because my axis of symmetry tells me that if I get a point, for example, here, I'm going to have a point on the other side of my axis of symmetry the same distance away. If you look, I have 1, 2 boxes away. This is 1, 2 boxes away. They are symmetrical. So that's the advantage of the axis of symmetry. Okay? Now, if we were to take this value and find our vertex, right? We said to find a vertex, we take our axis of symmetry. That's our x-coordinate, so 0. And then I plug that number into my equation. Well, if I plug that in here, it would be negative 2 times 0 squared. So this whole thing would be 0 plus 1 would be 1. All right. So at 0, 1, that's my vertex. I also know that the 1 is my y-intercept, which end up being 2 of the same. Okay, so in this case, when I found my axis of symmetry and my vertex, it only gave me 1 point, so I need to try finding something else. And when we do a parabola, we always need to have a minimum of 3 points, and our vertex should be one of those points. All right, so I'm going to plug something else in. How about, let's say, 2, okay? So if I plug in 2, this would be negative 2 times 2 squared plus 1. So this would be 4 times negative 2 would be negative 8, plus 1 is negative 7. So at 2, I'm at negative 7. All right. Again, guys, this is where your axis of symmetry comes in. This point was 1, 2 away from my vertex, or my axis of symmetry. So if I go 1, 2 away in the other direction, I'm going to get the exact same value. So at negative 2, I'm at negative 7. And now I can draw my graph. Okay. Now, why does this one open down? What do you notice about our leading coefficient? The number in front is negative. So that means our graph will open down. All right. Another one here. Let's go ahead and let's find our axis of symmetry first and your vertex. So why don't you go ahead and pause your video, see if you can come up with those on your own. All right, when I find my axis of symmetry, is at negative 1. When I plug negative 1 into my equation, I get out negative 4. All right, so now I have my vertex. So we could go ahead and graph some more. And again, okay, let's use this value here. This is our y-intercept. We know our graph's going to cross at negative 3. And hey, we don't even need to do an xy chart now because I have a point, right, not on my axis of symmetry. I know this one's 1 away. So if I go 1 away in the other direction, that's going to give me a point at the same height. So I know my graph's going to look roughly like this. All right, let's do. It's talking about a few other things with your graphs that we just need to mention. All right, and we talked about this just a little bit before. Is that when your leading coefficient is positive, so your ax squared plus bx plus c. When a is positive, that means your graph's going to open up. And if your graph opens up, that means your vertex is going to be at the bottom of your graph, which is what we call a minimum value. Now, if your leading coefficient is negative, so if this a value is negative, your graph is going to open down, which means your vertex is going to be the maximum value of your equation, or the highest point that this reaches. Okay. And where that comes into play is this idea of domain and range. And we've talked about that before, but it's been a little while, so just to recap here. So things that limit our domain, dividing by 0. Okay, well, if I ever have x squared plus bx plus c, am I ever dividing by an x? So no, this one can't happen. Okay, do I have a square root anywhere in my equation? I don't. So if those are the only things that limit my domain, am I going to have a limited domain here? And no. So this is where we're going to say our domain of our function is always all real numbers. Okay, so if we ask you for a domain for any equation, it's all real numbers. Now, what's your range going to look like? Okay, well, again, this determines if your graph opens up or if your graph opens down. If my graph opens up, it's going to be all y values that are greater than or equal to whatever that value is here at my vertex. If my graph opens down, It's y values that are less than or equal to whatever the y value is of my vertex. All right, so we got one last graph we want to go ahead and try, and I'm asking you for just a couple extra things on this one. But let's go ahead and pause your video and see if you can do this one on your own. All right, so if we find our axis of symmetry, again, it's the opposite of our b value, so negative, -8, over 2 times our a value, which is -2. We end up with -2. So that is our axis of symmetry. That's why I have my dotted line here. If I plug -2 into my equation, I end up with a +6. So that's the y coordinate of my vertex. So -2, 6 is my vertex. Using my graph, since it is in standard form, I know that my y-intercept is going to be -2. So it crosses my y-axis at -2. And where my other point comes from is, again, this is 2 spots away from my axis of symmetry. So if I go 2 in the other direction, I'm going to have a point of that same height. So my range, or domain, of course, all real numbers. My range, since my graph opens down, I get all y values that are less than this number. So y is less than or equal to 6.